One of the things that we can learn about atoms from their orbitals is about their atomic size. We know that in our previous studies of atoms, we have figured out that they have this nucleus, and the nucleus is a tiny and heavy thing compared to the rest of the atom anyway, where all of our protons and neutrons are, and so overall it has this positive charge. And then somewhere outside here we have electrons, and they have this kind of cloud-like existence. But we can also see that it is it's the electron area of the clouds that is how atoms interact with each other. Because if you have something that has some positive character in the middle and some negative character outside, and it approaches another atom that also has positive character in its nucleus and negative outside, then it's going to feel some opposing forces. The electrons are going to repel each other, but the electrons and the nuclei are going to attract each other. So, depending on how big these atoms are and how big their nuclei are, the amount of repelling and attracting forces is going to also be affected. So, how big is the electron cloud around an atom? There are two factors that affect atom size. One of them is which orbitals the electrons are in, so number of electron orbitals, which really means number of electrons. And the second one is how many protons, which I'm going to remind you is the atomic number, and we use a capital letter Z. So this is called the nuclear charge, just as a reminder. So we can get an idea about how the number of electrons affects the size of the atom by refreshing on what we saw with the shape of these mathematical functions for the Schrödinger equation. And really what we want to do is we want to look at the square, because the peaks, so the tallest peak was where we had the most likely location for the electron. So we can look at these wave functions, and we can look at this psi squared part of the wave function and see how the position of the electron is affected by which orbital it's in. So let's go ahead and switch over and take a look at some pictures of those. All right, so this is the probability function just in 2 dimensions, and we have the 1s orbital highlighted on this particular graph. So what I want you to notice here is that this x-axis, this is the distance from the origin, or from the nucleus. And this is specifically for hydrogen, but we can model it for all atoms just fine. So notice that here we are at the 1s orbital, and as we go further away from the nucleus, so as we add more electrons, our electrons are going to be further and further from the nucleus. So here we go, we've got some 3D, 3P, 3S, and notice that our wave functions and where those electrons are is going to get further and further from the nucleus as we add electrons into these higher and higher energy level orbitals. So depending on how many electrons we have present, like these will start to switch around a bit, but you get the idea that higher energy orbitals will have their electrons further from the nucleus. This means that the atoms will be larger. So if they have more electrons, then the atoms are likely to be larger than if they have fewer electrons. This is only one of the possible effects here that we have, and we need to explore it just a little bit more. So first, let's take a look at the atomic size of some atoms. The short way for us to think about this is not so much just about if they have more electrons, but if the atom has a higher shell, the electrons will be further away from the nucleus. So let's take a look at some atomic sizes for some of the alkaline earth metals and the alkaline metals. So let's just look at lithium and sodium and potassium and remember what their electron configurations are like just as a review before we do this. So remember that lithium has a helium core and then its valence electron is 2s1. Sodium has a neon core and its valence electron is 3s1. And potassium has an argon core and its valence electron is 4s1. So that's what I mean about adding a higher shell. That when we look at lithium, this is like helium plus the n equals 2 shell. We've added another shell. So this is going to be larger than helium, right? Sodium is like neon, and then we add the n equals 3 shell. So sodium is going to be larger than neon. Argon is our core, and then we add the n equals 4 shell for that next electron. And so we expect potassium to be larger than argon as well. So let's go take a look. All right, this is a close-up of figure 7.37 from the textbook. And what we have here are the atomic radii listed in picometers. So we'll review radius and picometers in just a second, but you can see that these numbers are all relative to each other. So we were just talking about the size of lithium, sodium, and potassium, and how lithium was going to be larger than helium because we added the n equals 2 shell. So you can see that happening really clearly. Helium here had 32 picometers for its radius, and we've just bumped it up a bunch, up to 152 picometers. So when we go and add a next shell up to sodium, then we increase it a little bit more. Sodium is, as promised, a lot bigger than neon. The same thing is true with potassium. Potassium is bigger than sodium because we've added that n is equal to 4 shell, and it's much bigger than argon, which was the noble gas core right before it. So we can see with these atomic radii that especially as you look down a column in a periodic table, we are adding an extra shell of electrons. And when we add an extra shell of electrons, the electron that goes into that shell, or the electrons, if we aren't just in that first column here, those electrons are going to be much further away from the nucleus, and so that atom is going to be much bigger. And this is our first periodic trend. This is a trend that we see on the periodic table that we can observe very clearly. As we go down a group in the periodic table, the atoms get larger and larger because we're adding more and more electron shells. So this is the first of the two factors that I wanted to talk to you about with respect to atom size. And that is adding the extra shell increases the atom size. But as you look at these this little chart here, you can see that we've got a little interruption where we don't look at the transition metals at all. We're just looking at the P group here on the left and on the the S group on the left and the P group on the right-hand side here. So these are just the main group elements. And the reason why we're focusing on the main group elements is that this trend in atomic size, or these two trends that we're observing in the atomic size, are most obvious when we look at just the main group elements. So you can clearly see the atoms increasing as you go down a group in the periodic table. What else can you see? Take a look across the periodic table in this row or period. You can see that these atoms are decreasing as we go across the periodic table for the most part. There's a few little inconsistencies, but we're not going to worry about a few little blips in here. Okay, we're looking at big trends. So as we go down a group, atoms are increasing, but as we go across the period, atoms are decreasing in size. So let's talk about that part of it as well. So when we looked at that periodic table, we know that down a column, down a group in the periodic table, what we're doing is we're adding a new shell. And so that increases the size. And that is the first of the two characteristics that I pointed out to you, that as we add a new shell, this increases the size. But the second factor I said had to do with the effective or the nuclear charge. The nuclear charge, Z, is the number of protons. So let's think about what's happening inside a hydrogen atom versus a helium atom. In a hydrogen atom, our electron configuration is 1s1, and in helium it's 1s2. And so we know that we have one proton and one electron in this hydrogen atom. We have 2 protons, 2 neutrons, and 2 electrons in this standard helium atom. And so if we think about what's going on in this atom, I have a nucleus that has a +1 charge, and then I have an electron in its cloud, and it's going to be feeling a certain amount of electrostatic attraction here, right? And we know that the attraction is based on the fact that we have one electron and it's interacting with one proton. And so we have a Coulombic attraction that's, +1, -1, and they pull on each other. So in helium, we have something pretty similar, but we have 2+ in our nucleus for our total charge here, and we have 2 electrons. And so think about what's going to happen. Even if I have these 2 electrons repelling each other a little bit, they're going to actually be pulled more strongly because there are 2 electrons, but each electron is sort of individual. So we kind of have one electron and another electron, but we have 2 protons in the nucleus. They are both in the 1s shell, and so as a result of this increased attraction from this larger nucleus, we actually have these electrons be pulled in a little bit more strongly because they have a larger nuclear charge. So we have a larger nuclear charge, we have the same electron shell, so we have a smaller atom. And this is what's happening across the row in the periodic table. If we are looking at, here, let's go back to our image. If we are looking at the atoms across a row in the periodic table, we can see that as we go from lithium to beryllium and so on and so forth, we're adding a proton to each of the elements as we go across toward neon. Each one of these is larger by 1 proton. But we're still in the n is equal to 2 shell. So all of our electrons are in that 2s and 2p shell. which means that our electrons, our orbitals, are not hugely different from each other in terms of how far those electrons are out from the nucleus and how far away they are. And so as we add more protons, the electrons in that n equal 2 shell are getting pulled a little more tightly toward the nucleus. So these atoms are getting smaller because the nuclear charge is increasing. And then as we go to n equals 3, the same kind of thing happens. We have at first a new shell with not very many electrons in it. And so those electrons are pretty far away from the nucleus. We're going to talk about why that is in a minute as well, why they're much further away. And as we add more protons to the nucleus without having our electrons be much further away, those electrons are going to be more and more strongly pulled toward the nucleus. So our atoms are decreasing in size as long as we're staying in the same set of electron shells. So that's our second part of our periodic trend, that the atomic size periodic trend says that atoms increase in size down the periodic table mostly, and they decrease across the periodic table mostly. These are trends, not laws, so we're just saying generally speaking. Atom size increases down the periodic table, atom size decreases across the periodic table. So I was just about to tell you why when we go from argon to potassium, our atom size increases so much. And the reason for that is shielding. So if we think about these electrons in the 1s orbital outside of the nucleus, being in a 1s orbital in an atom is kind of like being in the front row of a concert. You want to get as close to the stage of the concert as possible without actually being on the stage, because then you'd get taken away by the security guards, right? So we don't want to do that. We can't actually coexist with the stage. We have to just try and get as close as we possibly can. So if you have the nucleus and you are in the front row because you're in the n equals 1, then you have huge amounts of access and you feel very strong attractive forces to that nucleus with its nuclear charge. But now let's imagine that you're just kind of in the middle. You still are super excited to be at this concert, but the folks in the n is equal to 1 shell, they produce a certain amount of shielding. Shielding means that they are shielding you a little bit from the awesomeness that is the nucleus, or, your favorite performer on the stage. And so they're still going to be feeling a lot of attraction to that nucleus, but they're feeling a little bit less. So they experience an effective nuclear charge that is less than the actual nuclear charge. Okay? And if you are even in a larger atom, and you're in maybe an n is equal to 3 shell, or an n is equal to 2, or n equals to 4, or whatever, the further away those electrons are, the less, I'm going to call this ZF prime, because this is going to be even less than the amount of nuclear charge that these n is equal to 2 electrons are feeling. There's going to be even more shielding from the electrons. So when you go from something like argon to potassium, you have these electrons here in the n is equal to 2 have been pulled closer and closer and closer to the nucleus. And then you add an n is equal to 3 shell, and you only have 1 electron in that n is equal to 3 shell. And the n is equal to 3 shell doesn't see a lot of attraction for the nucleus because of all the shielding that's happening in front of it from the rest of those electrons. And the nucleus isn't very much bigger from argon to potassium. It's just added one more proton. And so this electron is feeling some attractive force, of course, but it's also still quite a bit further from the nucleus because we added that extra shell. Okay? So hopefully this analogy works for you okay. The main idea for atomic size is still just right here. So my description here about the effective nuclear charge is just to kind of help it make some reasonable amount of sense. All right. So we've got 2 more periodic trends that we're going to talk about, but I'm going to save them for the next video. So our first description here of periodic trends is just atomic size. And of course, when we're talking about radius, we're talking about the distance from the nucleus to the outer area of our atom. And this again would be measured on probably like the 90% probability surface, maybe the 95%. All right, so next up is going to be ionization energy and electron affinity.